Yeah, I mean.
Good morning, everyone. We have about 3 minutes before we'll start. Are there any questions while we're waiting? The most common question so far has been, can we switch lab sections? And I don't have a problem with switching lab sections as long as it's not overwhelmingly lopsided with 40 students on Mondays and 7 students on Wednesdays. But I do suggest that, or I would prefer that you stick with one lab section. Pick one and choose it. The lab sections will be largely the same, Mondays and Wednesdays. Labs for clarification go 2:30 to 5:15. We went a little long on Monday. This first lab's longer than most of them in terms of the instruction anyway. Okay, Julie, are you online? Okay, if there's no questions, I'm going to get started now. It's 9 o'clock. We have a big topic to cover today, simple linear regression. This is the main building block we're going to use for almost all the modeling that we're going to cover in this class. And I see 1, 2, 3. There's about 5 of you with your cameras on. I appreciate those of you who have turned your cameras on. It allows me to get a little feedback and nods once in a while too. So everybody can hear me? Okay, good. All right, so let me pull up my slides here. These are posted on Web Campus. And we're talking about simple linear regression. Before we start this, we talked about Henslow sparrows last time. And we were going to mention this first. So let me pull that up. Okay, so we had our preface. I'd like to hear some ideas on how should we design a study to inform fire management. And we talked about the considerations where Henslow sparrows are cryptic, sometimes hard to see them. There's lots of different sized grasslands at Big Oaks National Wildlife Refuge. We have to count Henslow sparrows from the road because, as I mentioned, Big Oaks was a former military ordnance testing facility, and there's bombs in most of the fields, and unexploded ordnance is a major issue. Some fields have lots of sparrows and others have few. So I would like to hear from you on some of the thoughts that you'd have in designing a survey to collect data to help inform management. And we'll revisit these topics throughout the semester with Henslow sparrows and with other applications, and learn the tools to adjust these. But as a starting point, let's talk about some of these considerations. All right. Let's see. I saw one hand here. Yeah, go ahead.
I did actually have a
Brianna.
question about this one. So talk about doing prescribed burns. What's the worry about setting off a bomb by doing the burns in the fields if you can't even go to the fields anyways?
If you walk in the fields, so you can, if you set a fire and a bomb goes off out in the field, that's less of an issue than if you're walking in the field and you step on a bomb and it goes off.
I know, but I'm sorry, I'm not worried as well, but that's something we should really take into consideration because What type of bombs did they use? How did they damage the habitat if they got set off? I mean,
Okay. Yeah, so is there a problem with bombs damaging the habitat? Actually, one of the reasons the habitat is good is because it had all this disturbance. So you're right in the short term that these bombs would damage the habitat for a small area, a few square meters. And this is about 50,000 acre refuge. So in the short term, you're right, it damages the habitat. But one thing that you may have learned in other habitat courses is that some types of habitat require frequent and recurring disturbances to maintain that habitat. And that's one of the reasons that big oaks was so good for these two grassland species. So crawfish frogs and Henslow sparrows are both grassland species. They require grasslands to survive. Now, these grasslands are interspersed in forested habitat. So if you let everything go and didn't do any management, the entire area would turn back into a forest. So this raises a whole nother ethical question on what should we actually do. Its natural state is a forest. However, we had this man-made disturbances that caused grasslands, and because they cause these grasslands, there's these rare species that are actually there. So you can make arguments on both sides on what would be good. Do we want to keep the grasslands? The easiest thing would be let everything go back to forest. And that's probably what the natural state is. But then we lose these huge populations of Henslow sparrows and crawfish frogs, which are very important for these populations. And this is something that refuge managers and Fish and Wildlife Service are debating and deciding on. And if they can't keep the grasslands, then they have some justification just for letting it go and saying, this is its natural state. We're going to do this anyway. And these types of high-level questions often change with administrations. So that brings up a good point. So let's assume that we want to stick with the status quo and keep the grasslands for now. That's what their management objectives are. They write these habitat management plans in the Fish and Wildlife Service that last for 20 years. And the current habitat management plan says, let's keep the grasslands. All right, how should we collect data to inform this management?
Is it just you have to do it from the road?
You have to do counts from the road, right? You have to collect data from the road. Yeah, okay, so that deals with that. So what types of counts can we do from the road? What types of surveys?
Like a site count, if that's what it's called. You can just point and see which ones, like how many sparrows you see.
Yeah, do counts from the road. One suggestion is like a point count. So you set up points. We were talking about in lab, we talked about today and Monday, we'll talk about point counts and how the breeding bird survey does point counts at 50 locations on a route. So that's one option. Definitely that is an option. So we get these counts, right? And let's think about these other considerations now. Lots of different fields. So you could develop these point counts from different fields. There's about 50 different fields. You could tangibly do point counts at every field. You have to count them from the road. How about this issue that Henslow sparrows are cryptic and sometimes hard to see? How might we address that?
Can you do audio surveys?
Audio surveys, yeah, can you elaborate on that a little bit?
Just, I don't know much about sparrows, but when I was doing owl surveys, we played owl calls and then just listened for a response. So you could just have like a microphone or something and listen and try to figure out how many there are there. Probably pick it up better than just your ears.
Okay, so some way to advance our physical ability to hear the animals. And then you mentioned playback devices too, so that is something that elicits a stronger response to the sparrows. So two things there. One thing, let's improve our ability to hear. Two, let's improve the probability that the sparrow is actually going to call if it's there. So those two considerations. And there, at this point, there are no wrong answers for this.
Got a couple suggestions in the comments too, or in
yeah.
the chat.
Okay. When I switch to sharing my screen, let me stop my screen sharing because I can't see those when I share my screen. All right, so look for evidence like NRES. Okay, Samir, can you expand on that?
I was just thinking in terms of if you can't actually do point counts because they're cryptic, then you can find other types of evidence of them living in the area.
Yeah, so a lot of wildlife surveys, you never actually see the animal. A friend of mine, Brian Gerber, studied Fusa in Madagascar for 2 years. He lived in Madagascar looking for Fusa. Never once saw his study species. He looked for other signs that proved they were there, but he never actually saw them. You can imagine his disappointment in studying a really cool carnivore for 2 years and never actually seeing it in a cool place. Yeah, so other types that show positive occupancy, that they're actually there. And for a lot of wildlife species, we have to do that. Let's see what else. Detect them from heat signatures. I like that. Technology. So use technology to advance our ability to see them. Heat signatures. So what about, there's also grasshopper sparrows in the field too. So now you have two about the same size birds. That brings up some issues when you are looking for heat signatures, where if we use a call, we can pretty positively identify them. But now if we use heat signatures, maybe there's some differences in the heat, maybe they're not. I'm not an expert on that type of technology, but you can imagine that there are probably some nuances and idiosyncrasies with using that.
So once you pick them up on a thermal camera, you should be able to pick them up just visually as well, because you'll know their location from there.
Okay, so you're talking about using them for the initial detection and then going in and using a different method to verify that they're actually there. So just as a cue to detect them.
Yeah. I was the
Okay.
one that suggested the thermal camera. I was just kind of playing off of that one.
You're following up on that. I like that.
Yeah.
Okay, I got a couple more people. Nice. Okay, so heat signatures follow up on, and so the heat signatures was from Steven. And Steven, you go by Stevie, I believe. Okay. Aerial surveys via drone. I like the potential of aerial surveys and drones. Some of my recent research has been trying to develop camera methods for improving surveys that use drones to get people out of there. It's one of the most dangerous jobs as wildlife scientists, is flying surveys. In Shepherdstown, West Virginia, they have the National Conservation Training Center. It's the headquarters of the U.S. Fish and Wildlife Service. And they have a wall there dedicated to all the wildlife biologists who have died in the line of duty. And I'd say like 90% of them are from flying surveys. Okay, drones. I like that idea. Drones are good, especially for these types of surveys. Maybe more.
How readily do the sparrows move between fields?
Good question. This is something we'll talk about in mark recapture. It's called closure. Do we assume that grasslands are closed, that if they're there, they're always going to be there? And this gets into the whole BIDE model, births, immigration, deaths, emigration. We can assume, and it's a fairly good assumption, that within one day, they'll be in that grassland all day. But if you wait a couple of weeks, they may move, and that presents serious challenges. I'll tell you, when they initially designed the survey, they did one survey in June and one survey in July. And what they found was drastically different counts in the grasslands between those months because of movements among grasslands. So it turns out that the study design that they developed for this violated that closure assumption, and that caused some serious issues for them being able to estimate how many sparrows there actually were. Catch and track them with GPS. Yeah, there are some GPS devices that are small enough for sparrows. The issue mainly with that is battery life. So the main restriction on GPS technology right now is battery size, and hopefully technology will relieve some of those issues.
I was actually reading about some GPS. I think it was for an Arctic species, and what they did is they made it solar powered, so it reacted to the sun. And that could be a way to kind of go around the battery issue if we're looking for long term.
Yeah, you're right. With Arctic geese, they have been able to follow them for a long time. So I have some collaborators in the Dixon field office working with migratory geese, and they use these GPS trackers for, and they have these solar panels on them, so they recharge automatically as long as it's not too cloudy over a long period of time. And then you can just keep the collars on over and over, and the battery life becomes less of an issue. Now, these are geese, so they can make them a little bigger, and they have these solar panels. I'm not sure yet on this about the status of the technology on solar recharging batteries for tiny little dicky birds. Using their own bird calls to draw them in. Yeah, that's good. Let's go back to that playback method. Let's see, GPS, call counts. Yep. Okay, very good ideas, very good thoughts. I like these. We'll keep a list of this, and we'll come back to a lot of these themes throughout the semester and how we deal with these types of idiosyncrasies when we're trying to count wildlife, because wildlife, one of the major development areas that we've worked on in the last 50 years is how do we detect species when they don't want to be detected. And actually wildlife has led the field in terms of method development for this specific problem. So a lot of the methods that are used at, for example, airports when they're screening for security, and known facial recognition deals with this issue of not being able to detect someone who doesn't want to be detected. And they've borrowed methods from the field of wildlife to try and do that. All right, so let's move on. We talked about that for 15 minutes. Let's get into simple linear regression. So I mentioned before that this class builds on each other successively. I'm going to, hey, Julie, can you monitor the comments on this? Because I can't see those when I'm sharing my screen.
Yeah.
Okay, thanks. And if you have any questions, please feel free to interrupt. All right, simple linear regression. This is the building blocks for our statistical modeling of wildlife populations. Here are the learning outcomes, what we need to learn from this lecture, take-home points. You'll need to understand why we use simple linear regression in wildlife science and the type of inference it can give us. You'll need to know the difference between our data, which we're going to call Y in this class, our covariates, X. So covariates are things we measure that we think are related to our response, Y. What parameters we're interested in. For simple linear regression, it's going to be beta 0, beta 1, and sigma squared. And residuals, epsilon. And we'll talk about these points in this lecture. You'll need to know how to write out a simple linear regression model in proper statistical notation, both in the general form and the fitted form. So we'll talk about what those two things are. And then next week in lab, we're going to use our statistical software to fit a simple linear regression model to real data and then interpret the output. And there's one example of that in this lecture as well. And it turns out it's very straightforward. All right, so let's start with an example. This goes back to what we talked about last lecture, and you see a headline in a news outlet. They make a claim, and we want to evaluate the validity of that claim. So this came out a couple years ago, and it said that, it came out January 31st, 2018, says survey shows Yellowstone elk herd at highest level since 05. So this article has, if you value a high population of elk, this article shows some optimism about elk herds in Yellowstone. So let's actually look at what data they used to, so I think last year I saw this article and I emailed a biologist at Yellowstone and I asked for some of the data they used to make this claim. And this is a subset of that data. We'll actually look at the full data set ranging back before 2006 when we talk about multiple linear regression. But here's a question. Has the Yellowstone elk population increased in abundance since 2005? And here are those data. We have year on the x-axis and y on, and counts of elk on the y-axis. And you see this claim here, let's see right here. This point is indeed higher than any other elk herd since, any other count since 2005. So it is the highest level, and that's what this claim is based on. So let's go back to simple linear regression and describe how we're going to use this model to describe the
lying naked in bed.
Okay. So let me go back to this here. We're going to use simple linear regression to quantify the relationship between our continuous response variable y and our predictor variable x. Our predictor variable is going to be year. We want to predict what the population is going to be in future years. And we want to know what the response variable is, the counts of elk. So this is our objective. And this is what we're going to use simple linear regression model to do. I mentioned this before that we're going to use y in this class to represent response data. We're going to try to stick to that as much as possible to avoid confusion. We're going to use x to represent covariate data, and this can be things like year, habitat quality, precipitation, anything that we want to examine the relationship between our data y and our covariate of interest x. All right, so what we want to do is learn something about the relationship between x and y. And for our x example, y are the counts of elk, and then x is the year. So we want to learn something about the relationship between time and how the elk population has changed. Here's something about x and y. X and y have been, we're assuming that the data have been collected already. We've already developed a survey to collect those data, and we have an Excel spreadsheet that has x and y in those, x and y in those data in that spreadsheet. What we don't know is the relationship between x and y. All right, let's talk about this word relationship here. What do we mean by that? In the case of observational data, a relationship does not mean a causal relationship. That is to say, the change in y was caused by a change in x. Unless we're able to do a controlled experiment. So this is something like you can do in the lab, where you've heard of experiments where all you do is change one variable, you keep everything else exactly the same, and you examine how changing one variable changes the response in your data. This is very hard to do in wildlife science. It's hard to randomize animals in the wild. It's hard to even see animals in the wild, much less randomize them. We don't know all the animals that are out there, so we can't randomly select a subset. So the vast majority of data in wildlife science are observational. And rarely can we actually do an experiment on those data. So we're rarely going to say that the change in y was caused by a change in x. Instead, we're going to say a change in y is correlated with a change in x. And we can use these correlations to support hypotheses, but they're not going to prove any hypotheses. Okay, so how do we quantify the relationship between a continuous response variable y and a predictor variable x? This is where our math and stats are going to come in. Right now we're talking about continuous response variables, but the same methods in simple linear regression apply for categorical variables, and I'm going to touch on an example with categorical variables and spotted owls later in this lecture. So in a calculus class you've taken, you study what mathematical functions are. There's some function of x. You have a function of x on the y-axis and an x on the x-axis. We're going to use those same functions. However, we'll never be able to find a mathematical function that describes wildlife data perfectly. Now, there's always going to be some uncertainty around a mathematical function, and you'll see what I mean by this in a future slide. The field of statistics is all about quantifying uncertainty. So we're going to need both mathematical functions and statistics to quantify uncertainty in those functions, and we're going to do that with simple linear regression. So here's the first mathematical function we're going to use, and that's the equation of a line. So here we use beta 0, beta 1, and x. Y is our response data. X is our predictor data. So for our elk example, Y are counts of elk, and X is the year. Beta 0 and beta 1 are the parameters we need to estimate. Those are the values that describe what the line actually looks like. If we change beta 0 and beta 1, we're going to get different line than the previous values of beta 0 and beta 1. I'm just going to check the waiting room quick. Okay, Julie, can you see the waiting room?
Yeah, I'll keep an eye on it.
Okay, no one's in there now?
Nope.
Okay, good. All right. Any questions about this so far? Oh, actually, I see Jevin Doherty. Okay. Any questions about this so far?
There's a question in chat.
Okay, if you can voice those questions, it makes it a lot easier because I can't see the questions when I'm sharing my screen.
Yeah, my question was, could you just do a brief definition of the response variable and the covariate variable?
Yeah, so our response variable is usually some quantity we're interested in. So in the case of elk, we're interested in the population size. So it's a quantity of interest for which we have data. The predictor variable, or the covariate x, is a value that we have information on that we think is related to the response variable. We're going to use the predictor variable to try and predict the response variable.
Thanks.
You're welcome. Okay. So we know what y is and we know what x is, but we don't necessarily know what the best values of beta 0 and beta 1 are. And those are going to determine what our line looks like. So we have to estimate what beta 0 and beta 1 are, and we're going to use our data to do that. Okay, so you've seen y equals mx plus b in previous classes. This is another way to write y equals beta 0 plus beta 1. If we go back to our equation here, beta 1 is equivalent to the m, and beta 0 is equivalent to the b. So in mathematics, they often write y equals mx plus b. In statistics, they always write y equals beta 0 plus beta 1x. Beta 0 is the intercept, and beta 1 is the slope. Okay, so another day has passed, still haven't used y equals mx plus b. And you can see this is extremely important. This tweeter got a lot of feedback for posting that. All right, so here's a couple examples, equation of a line. Let's set beta 0 and beta 1 equal to 1. Now what we're going to do is estimate what beta 0 and beta 1 are using our data in R, but we can just mess around with these values here and see what different values look like. So if the intercept equals 1, that's beta 0. that puts a point right here at x equals 0. And then if beta 1 equals the slope equals 1, we see the slope of this line equals 1. So a review of the equation of a line. Beta 1 equals rise over run. We can calculate that with 2 data points with our y's and x's from 2 data points. That gives us beta 1, and beta 0 is wherever it crosses the x-axis. We can change those values slightly to see how that changes the values of the line. Now, if our slope equals -1, that changes our line to be negative and going downwards instead of upwards. We still have the intercept at beta 0 equals 1. All right. Y equals beta 0 plus beta 1 x is a function. It's also called a mathematical model. If we know beta 0 and beta 1 and we give it a value of x, it's going to tell us exactly what the value of y is. There is no uncertainty in this function, and we call that deterministic. So a deterministic model is a function that does not address uncertainty. We'll talk about what uncertainty is in the next couple slides. So if it's deterministic and there is no uncertainty, if we know what x is, we know what y is, and vice versa. We know y and we know x. Beta 0 and beta 1 are called the parameters of the model. And in statistics, we estimate the parameters of the model using data. The model, the mathematical model in this case, is y equals beta 0 plus beta 1x. And this is what we're using to describe the relationship between x and y. So if we want to know what the relationship between x and y is, we use this function. If we know beta 0 and beta 1, we can give it any value of x, and that'll give us a value of y. All right, so far this is all mathematics and the equation of a line. Here are definitions of beta 0 and beta 1 and what they mean technically. Technically, beta 0 describes the value of y when x equals 0. We can see this in this mathematical form here because when we plug in 0 at x, this whole thing is going to equal 0, and all we're going to be left with is beta 0. So y is going to equal beta 0 when x equals 0. If x equals 1, it's going to equal something else. Beta 1 describes the change in y for 1 unit change in x. All right, so I've talked about beta 0 and beta 1 and how those are parameters that we want to estimate. So actually, how do we choose reasonable values of beta 0 and beta 1? And we can look at what different values of beta 0 and beta 1 do by looking at this animation here. Is this animation coming through on Zoom? Let's see, I can't see anyone.
Yes.
Yeah.
Okay, it is. All right. So you can see the values of beta 0 are changing. It's notching up every so many iterations. It jumps up. So this is beta 0. It's the value of this line at 0. And then what's changing more fast is the value of beta 1. The slope's changing. So now we have these Yellowstone elk data here. And what we want to do is describe a line that fits these data. How do we choose the values of beta 0 and beta 1 that best fit this data? And that's the question that we're trying to address. How do we choose the best values of our parameters, beta 0 and beta 1, that are going to best fit these data? Well, the simple answer is we plug in x and y and we let our statistical software do it. It's going to give us values. We're going to give it x and we're going to give it y, and it's going to give us feedback back that says, here's the best values of beta 0 and beta 1 for your data. Now let's talk a little bit about the statistics of this. If we go back here, no matter how we change beta 0 and beta 1, there is no possible way for this line to go through every single data point. If it was, we would have a perfect model that describes our data perfectly, and we would be able to predict exactly what the Yellowstone elk counts are going to be for any time period. However, when we actually fit this line, this red line to these data, at best, the line is going to go through probably 2 points. And none of the other points are going to be on the line. And that's where we move from a deterministic mathematical model to a statistical model. Okay, so no values of beta 0 and beta 1, no matter what we choose, are going to permit this model here, this mathematical model, to go through every point. So this deterministic function y equals beta 0 plus beta 1 x does not hold. Given this, we have to move beyond the field of calculus and mathematics and move into statistics because there's uncertainty in our data. Why don't, in terms of the biology of the system, why doesn't this function fit through every line? Well, it's because there are so many unmeasured environmental drivers that are going to influence elk counts that are not accounted for in this simple line. This unaccounted for drivers in elk population are called what we call residual error, and we're going to represent this with an epsilon. So what are some of these factors that prevent us from drawing a straight line through the data? All we have are information on elk numbers in a year. What else could possibly influence the elk population so we don't have a perfect relationship?
Changes in predator populations.
Yeah, exactly. The wolf population in Yellowstone, bear population.
Habitat quality.
Yeah, habitat quality. Exactly. Disease, yep. Precipitation, that affects habitat, I guess. Yeah, lots of things that describe why we don't have this perfect relationship. Things we don't even know about, things science has not yet told us of why this population can't be perfect. As we learn more and more, hopefully we could do better and better to get our line closer to those dots. And we'll do that when we talk about multiple linear regression. But anyway, there's all this unmeasured environmental drivers that's causing the elk population to go up and down. And when we can't model those, we're going to call that residual error and represent it with epsilon. However, we can let the model y equals beta 0 plus beta 1x, as simple as it is, describe the average relationship between x and y. This is also called the expected value between x and y. And what we're going to do is describe the average change in population from year to year using the simple linear regression. And we're going to quantify the error in the system. All right, so now we're actually getting to the statistics. So let's spend a little bit of time here and describe this, because this becomes important. Let's see. There we go. Let's see if this works here. All right, can you see that screen here? Yep, okay.
Yes.
All right, so let's just change the example slightly to get away from elk and talk about simple linear regression, but in another example, just to offer more diversity here. So let's say we're interested in how spotted owl home range size changes with the number of patches within its home range size. So why would we be interested in this question? Well, ecological theory states that if an animal can get all of its all of its required resources in a small amount of area, that optimizes its fitness because it doesn't have to move around very far and expend a lot of energy trying to find the resources that are available. So if we think maybe habitat fragmentation increases the spotted owl home range size, then we may be able to say something about the relationship between habitat fragmentation as measured by the number of patches and spotted owl home range size and say, well, if the number of patches within the home range increases, it's fragmenting the landscape and it's lesser quality habitat, and spotted owls are going to have to cover a larger amount of area to survive and reproduce. So this is a hypothesis we could pose, and then we can collect some data. We could put some radio collars on spotted owls, follow them around, and measure their home range, and then count the number of patches within their home range. And we can get data on that, and we see this data. So this is our response variable y. Let's see, response variable y here is a continuous random variable because size changes between, it's continuous between 0 and however big it could possibly be. And our number of patches is also continuous. So we have continuous variables here. We have this relationship, and we're interested in a line that describes this relationship. So just by eyeballing it, I could draw this line here. It may not be exactly perfect, but you get the idea. We'd actually use statistical software to fit that line. We're going to get our intercept here, beta 0. The rise over run here is going to be our slope. And now we have what we call the expected relationship between the number of patches and spotted owl home range size, or the average relationship. So given our data and our model, this line here describes the average relationship. However, as we mentioned before, it doesn't describe, actually the way I drew this, it doesn't go through any of the points. There's a distance between each point here and our fitted model. So this line is, we'll call this y hat equals beta 0 plus beta 1 x, say I. Sometimes I also use mu to describe this relationship. Actually, I never use y hat. So in statistics a lot, they use y hat. In wildlife, we tend to use mu more. So let's say mu equals beta 0 plus beta 1 xi. We know what beta 0 is. We've talked about that. We know what beta 1 is. Mu is this line here. It's this mathematical line. So if I give you a value of x, let's say right here, value of x, choose a different color, value of x right here, you can tell me what the value of mu is by drawing a line and going over to this value here. So this would be our mu for this specific value of x. And we use this I subscript to describe specific values. But this doesn't tell us what the yi's are all of our points. So how do we actually describe what those yi's are using this value of this relationship here? Well, let's add one more thing to this. And let's call this the distance between the line and the actual point. We're going to call that our error, epsilon. So that's our I. So now if I want a function that describes where this point is right here, I can say that value, we'll call this I equal to 1. So we'll say y1 equals this line here. So we first go to this line, which is beta 0 plus beta 1 xi, where xi is going to be this point, and I'm going to erase this. I'm going to erase our previous example here. Y1 equals beta 0, so this is x1. Y1 equals beta 0 plus beta 1 x1, so that gets us here. Now we need to add on this little part here to actually get to our data point. So plus epsilon 1. So this point here is y1, this is x1, and this is our mu1, our value of mu1. Let's do one more example, and then we'll see if there are any questions on this. All right, let's look at this point here, and let's say this is y2. So this point here is y2. How do we describe what y2 equals? Well, first we have to figure out what x2 is. x2 is going to be the x value right below the point. So here's x2. So y2 equals beta 0 plus beta 1 times x2. And then we're going to add the error here, the distance between the line and the point, and we call this epsilon 2 plus epsilon 2. And that gives us an equation that describes where our points are in this plot. Okay, are there any questions on that? And I can stop sharing this so I can look at the comments.
When the
Okay.
points are under the line, is the epsilon negative?
It is negative, yep. So for our second example, we would say y2 equals beta 0 plus beta 1 x2 plus epsilon 2. And I'll just put on a value of epsilon here. We'll say epsilon is -1, where epsilon 2 equals -1. So we're adding a negative here.
Can you share your screen again, Perry?
Yeah. That's the danger in going and looking at the chat section. All right, so this is what I just wrote down. We say y2 equals beta 0 plus beta 1 x2 plus epsilon 2, where epsilon 2 is negative, it's below the line here. So epsilon 2 equals -1. We're adding a negative, which is the same as subtracting. Okay, any other questions? All right, then I'll continue. Okay, so we have these equations here. We talked about these in our learning objectives at the very beginning. We wanted to be able to describe what our response data is, so our y's, what our covariate data, our x's are, and we put these on our x and y axis, what our parameters are, beta 0 and beta 1. We haven't talked about sigma squared yet. And what our residuals are, our epsilons. The difference between the fitted line and the data are our residuals. Okay. And here's a more formal slide of exactly what we just talked about here. We didn't talk about what this I subscripts mean formally yet. We just kind of mentioned them in this last one. I's just keep track of actually what data point we're talking about. And we can use I in general to describe all of them. But if we're interested in one data point, you can think of I as the row, which row we're in an Excel table. So for our first row, I equals 1. For our second row, I equals 2. We don't want to rewrite this equation here 14 times, for example. So instead of just writing it once, we just put an I here and say I represents I equals 1 to however many data we have. That's oftentimes a point of confusion when writing out these. What does that little I mean? It's just a way of keeping track of and shortening how we write out this model for all of our different data points. So you can think of I as the rows in an Excel table. So I is going to equal 1 to all how many rows you have, how many data points you have, and we often use n for our sample size. All right, now we haven't said anything about how big epsilon i's are or how we could describe these statistically. But when we use simple linear regression, we assume that the errors, epsilon I, are distributed as a normal distribution that has a mean 0 and a variance equal to sigma squared. There's a lot of practice questions in the practice problems that try and make this more explicit, using R code to try and do simulations and to show what this actually means in terms of computer text. But this is one of the assumptions of simple linear regression model, that errors are independent and identically distributed, and the distribution they follow is normal, that has a mean 0 and a variance sigma squared. So let's talk about sigma squared. We said one of the objectives of this lecture was to describe the parameters, and one of those parameters of simple linear regression is sigma squared. Sigma squared describes how far away these points are from the line. If they're very close to the line, sigma squared is small. If they're very far away from the line, sigma squared is big. R also estimates what sigma squared is given the data. It'll tell us what that is. I'm out of time. Okay, we will touch on this. We'll start off on this on Monday. We have about 5 slides left. And I'm happy to stick around if there are any questions on what we've covered so far, but we'll review this and then touch on these last 5 slides, actually last 4 slides, starting Monday morning. Okay, thanks. I do have office hours right now, and I'll just stay on this Zoom call for office hours.
Have a good day.
Thanks, you too. Resume recording. Okay, so I'm just going to reiterate that question. The question was, in our mathematical model, yi represented the line. So I'm going to share my screen. Okay, the question was, when we were talking about yi first in terms of a mathematical model, yi represented the line. But then when we start having data and we're talking more of a statistical model, does mu I replace this yi? And the answer is yes. Mu I is the new yi here. And yi means something different. Yi means mu I plus our residuals.
Because it's replacing the value I see now. That makes sense.
Yeah, so in mathematics, y means the value on the function. In statistics, y we use for the data, which includes both the function and the distance between the data and the line, this distance here. So instead of using yi to represent the line, we're using mu I to represent the line. And then yi is the line plus that error that is unaccounted for.
Yeah. Okay, great. That makes more sense when it's labeled out like that.
Yeah, good question.
Thank you.
You're welcome. Okay.